In this video, we'll explore flexible, non-parametric modeling in higher dimensions using generalized additive models. Consider an example. Suppose we want to model y, the number of bike share riders on a given day, by x1, the temperature on that day. Notice here that ridership tends to increase with temperature, but starts to dip when it gets really hot. So, though a simple linear regression model might be a good start, a lowess model would better capture this complexity. The lowess model represents the relationship between ridership and temperature by some smooth, non-parametric function f. And just as we hoped, this function does indeed capture the dip in ridership on hot days. We can similarly build a lowess model of ridership versus humidity. Notice here that ridership moderately increases as humidity increases, but then declines once humidity surpasses roughly 60%. So if temperature and humidity both tell us something about ridership, perhaps we can do even better by including them both. To this end, we can stick both predictors into a single model through their own smooth functions f. Specifically, we can write ridership as some intercept or baseline ridership beta 0, plus some smooth function f1 of temperature, plus some smooth function f2 of humidity, plus a residual error epsilon. And this is a generalized additive model, or GAM. GAMs are flexible, non-linear models that, unlike lowess, can handle more than one predictor. And each of these predictors is included in the model through some arbitrary function f. Let's consider some examples of what these smooth functions might look like and why I call them arbitrary. First, it might turn out that the function f1 of x1 is some coefficient beta 1 times x1, and the function f2 of x2 is some coefficient beta 2 times x2. But this is just our usual linear regression model. Thus, linear regression happens to be a very special or simple case of GAMs. As another example, suppose that our function of x1 is e to the x1, and our function of x2 is 5 times the square root of x2. That is, the functions fx might be represented by very specific equations. But in practice, this would be rare. It would typically be very difficult to define these functions so precisely. In fact, the whole motivation behind the GAM algorithm is to help us automate the estimation of our model, mainly to help us avoid having to identify such specific functions. Thus, in practice, the GAM algorithm does not make any specific parametric assumptions about the predictor functions. Instead, it estimates these using the lowess or another non-parametric smoothing algorithm. Though the details of this estimation process are more complicated, the main idea is this. To estimate or build the function f1 of our first predictor x1, you might assume that we'd use lowess to directly model y by x1 in particular. But we don't. If we did directly model y by x1, we'd completely ignore the fact that there's another predictor in our model. Instead, we start our estimation of function f1 for predictor x1 by modeling y by the other predictor, x2. We then calculate the residuals from this model. Now, remember that residuals are essentially prediction errors. They represent the features of y that were not explained by the predictor x2. But some of these leftover features might be explained by the other predictor, x1. To this end, we then model these residuals or leftovers by x1, for example using the lowess algorithm. This produces the function f1. Now, since f1 is technically modeling some leftover residuals, it doesn't tell us about the direct relationship between y and x1. But it does something better and more powerful. It describes the relationship between y and x1 when controlling for the other predictor x2. This interpretation might ring a bell. It's similar to when we interpret predictor coefficients in a linear regression model that contains multiple predictors. Let's try to build some more intuition for these concepts by applying the GAM algorithm to our bikes data. Our goal here was to model ridership by some baseline ridership beta 0, plus some function f1 of temperature, plus some function f2 of humidity. Though these functions f can't be represented by specific formulas, that is, there's no closed form representation, they can be explored graphically. Plotted here are the functions f1 and f2 for our two predictors, temperature on the left and humidity on the right. The x-axes look familiar. Mainly, our function f1 spans temperatures from roughly 40 to 110 degrees. And our function f2 spans humidity observations from roughly 25% to roughly 95%. What might surprise you are the y-axes. These are not on the scale of ridership. Mainly, we know ridership can't be negative. Rather, these axes are on the scale of the residuals that, in turn, represent the behavior in ridership that's unexplained by the other predictor. That said, if we focus on just the general shape of these smooth functions, they do still provide insight into the relationship of ridership with our two predictors. For example, consider the plot related to temperature at left. The shape of this plot indicates that when controlling for humidity, ridership tends to steadily increase as temperature increases, but once it gets really hot, around 80 degrees, ridership steadily declines. The humidity plot at the right indicates that when controlling for temperature, ridership is pretty steady when humidity levels are below 60%. But beyond that, ridership starts to decline pretty rapidly. At this point, you might be experiencing déjà vu. We made similar observations at the beginning of this video for the more simple lowess models. So let's compare these results side by side. Starting with the temperature predictor. The GAM results at the top appear pretty similar to the lowess results at the bottom. However, their interpretations are different. Whereas the GAM results examine the relationship between ridership and temperature when controlling for humidity, the lowess results examine the relationship between ridership and temperature while completely ignoring humidity. The fact that these results are similar suggests that temperature includes unique information about ridership that can't also be explained by humidity. Thus, when we control for humidity, it doesn't change our understanding necessarily of that relationship. Next, consider the GAM and lowess results for the humidity predictor. Again, the GAM explores the relationship between ridership and humidity while controlling for temperature, while the lowess model completely ignores temperature. And though both models exhibit a decline in ridership once humidity exceeds roughly 60%, there are some differences for the lower humidity levels. Mainly, the GAM exhibits flat ridership in this area, whereas the lowess exhibits a moderate increase. So what explains the difference here? Well, my theory is that lower humidities might also correspond to warmer temperatures, and we've observed earlier that warmer temperatures are associated with higher ridership. Thus, when we don't control for temperature, as we didn't in this lowess model, ridership might appear to increase with humidity, where this increase is actually explained by temperature. We'll continue to learn more about the GAM algorithm and address one big open question that we've completely ignored up to this point. With all of the complex moving parts involved, how do we tune the GAM algorithm? Good question.